Okay.
All right, so this is the PDR presentation for Team 3 of the NASA Space Academy Level 1. And our mission statement for our project was to gain insight into the atmospheric evolution of Mars by examining trapped gases in Mars's north polar ice cap. And our primary goal is to land a payload safely and efficiently on Mars's north polar cap. And we plan to sample and analyze ice samples from various depths and analyze the chemical composition of the volatiles present in the gas. The gas composition will give insight into the evolution of the Mars atmosphere. And just a summary of the members of the team. I'm Nate Santana. I'm a Drexel University student and a physics major.
I'm Zachary McNeely. I go to Jefferson Community College, and I'm an engineering major.
I'm Sharda. I go to Johns Hopkins University, and I'm a chemical engineering major and an earth and planetary sciences minor.
My name is Ofan. I'm a physics major, and I study at Drexel University.
I'm Josh. I'm a physics major, and I study at Drexel University.
My name is Gina Cologne, and I'm a junior at Rensselaer Polytechnic Institute, majoring in aerospace engineering.
And yeah, as far as the two other members, they weren't able to make it tonight. So to kick things off, we have our descent and lander summary. Just the sum of the masses of the landing equipment and scientific payload couldn't exceed 500 grams. And also mass limitations for our payload must not exceed a volume of 30 by 30 by 30 centimeters. Plus, in addition to the size requirements, the payload must also rely purely on mechanical systems. So it can't have any electronical systems at all. Electronic systems can easily pick up interference and act less deterministically than mechanical parts. And the payload summary just goes over what types of tools our payload would have. That will be the robotic arm, which was inherited from the Phoenix lander, and the robotic arm camera, also inherited from the Phoenix lander. The thermal and evolved gas analyzer, also from the Phoenix lander, and the surface stereo imager.
When it comes to the evolution of our project, our first challenge was choosing a specific landing zone. Some possible landing zones we had in mind were the Gusev crater, the Kostrova crater, and the Islidis planitia. Then we had to make some changes to the payload criteria. Originally, our tools included cameras that were specialized in locating minerals such as hematite, carbonates, olivine, and amphiboles. We made a lot of changes to the mission experiment implementation plan. Our original research route was elemental analysis of recurring slope linii, a search for hematite, which was not possible because of logistic difficulties and danger for the equipment due to the change in seasons. After all, our group decided to drill core sample of ice and perform spectroscopical analysis on the gases trapped inside, with the intention of dating the atmospheric makeup of Mars based on how deep the bubbles exist.
This didn't make it onto the PowerPoint, but we also selected our final landing site on the North Pole of Mars because it has large ice dunes, which we figured were smooth places to land our spacecraft and take samples from. And we picked a spot directly in the center of the North Pole because the North Pole is known to move in the ice is known to flow in a spiral motion, especially near at lower latitudes due to Coriolis forces. And the center of the ice cap would be least affected by that.
Yeah, exactly. So moving on to descent and lander criteria. When it comes to mission performance, our predictions are that there will be a safe deployment of the lander on the polar surface of Mars. Then the lander will be navigated on the surface in search of appropriate and interesting sampling sites for chemical analysis of the ice located there. We're going to utilize the balloon mechanism in order to safely land the payload. And once the payload is on the ground, we're going to use rigid aluminum wheels that also contain titanium spokes. The surface stereo imager will be used for imaging of the site and protection of the lander from dangerous terrain, dust, or other hazards. Up next, we have the payload integration. So our balloon gondola will be mounted on top of the payload for easy deployment during the descent into Mars' atmosphere, which will happen at a specific altitude.
So our payload will be within the lander right here, and it'll drop down from this little hatch right here. And then the dimensions, again, for this will be 30 by 30 by 30 centimeters. And the lander itself has to be under 500 grams. And I believe we were at 327 grams. And our largest problems with it so far was to cut weight, get under that. But we achieved that. And then the arm also for here is the main shovel, as you can see, with 3 parts right here in the shovel to scoop up samples of soil and ice. And later on, we'd add our scientific equipment to analyze that.
These are the criteria for our payload and how we selected, designed, and verified this experiment. Actually, all of the payload science experiments in our model are modeled after the ones in the Phoenix Mars lander. And we did this because it would be easy to verify that the instruments will perform properly. Also, our mission is similar to that of the Phoenix Mars lander, since it was used to sample ice and soil, not directly from the polar ice caps, but still on Mars. The science value of our experiment is that we should find geological evidence of the presence of large amounts of liquid water on the Martian surface, as well as we should find theory for existence of liquid water on Mars. On Earth, greenhouse gases can be extracted from ice cores to study changes in the atmosphere, and we are attempting to use the same approach on Martian ices in order to track the evolution of the Martian atmosphere.
So to go more in depth into the science instruments on our payload, we'll first talk about our robotic arm. So our robotic arm is the instrument that picks up our sample. It creates trenches at various depths so we can sample the ice at different depths, so basically through time. It's got various tools to penetrate through the hard icy surface. It has ripper tines and serrated blades to do that. And it also has a scoop that will ultimately capture our sample and deliver it to our thermal and gas analyzer instrument for analysis. Next, we have our robotic arm camera, which is a camera that's attached to the robotic arm just above the scoop. So it can take visual images of our sampling site, get some really detailed images of the texture and layering of the floor and sidewalls of the trench, so we can understand a little more of the character of the site we're sampling at. It's also helpful for verification of sample collection, making sure that we have a sample and we have a sample that we want. It's equipped with 2 lighting assemblies that will provide illumination of the target, and at closest focus, the image resolution is 23 microns per pixel. After that, we have our thermal and evolved gas analyzer. So it's composed of a differential scanning calorimeter and a mass spectrometer. The samples are first delivered to the differential scanning calorimeter. It contains 8 furnaces, so we can have up to 8 samples, approximately 5 centimeters in length and 2 millimeters in diameter. It gradually vaporizes the samples to 1,000 degrees Celsius, and the heat flow data will show us phase transitions of different materials in the sample and tell us a bit of the chemical character of the sample we're studying. The gases from the calorimeter are then moved to the mass spectrometer, which measures the chemical composition of the evolved gases. It has a sensitivity of up to 10 parts per billion, so it can give us some really fine detail on the trace gases that are present in the ice. And our last science instrument is our surface stereo imager. So this is an imager that provides really high-resolution stereo panoramic images of the lander's surroundings. So while the robotic arm camera gave detailed pictures of the trench that the arm was digging in, this one gives information on the surroundings and the surface. It has optical and infrared filters to provide images at different geologically interesting wavelengths. It's positioned about 2 meters above the ground, and the images will enable us to guide the trenching operations of the robotic arm. Because of its 2 openings that function like 2 eyes on humans, we can get stereo images, which can help produce digital elevation models that will also support our digging site selection, because we want to make sure that we don't go somewhere too rocky or just dangerous. It can also estimate the density of atmospheric dust and the optical depth of airborne aerosols and the abundance of atmospheric water vapor. And these images, especially the data on atmospheric dust, is important because it will be used to assess the amount of dust on the spacecraft and to check for hazardous levels of deposited dust on the solar panels, because we want to make sure a spacecraft is safe and can return back home eventually.
Now, our activity plan is up next, and our activity plan basically helped us organize what parts of the project that needed to be accomplished. And that's starting at the finalizing our prototype of the CAD file and ending at the Earth mockup that we're going to build in Academy 2. And obviously, some activities took longer than others, like completing the results has a longer time period than, say, finalizing the prototype CAD file, which was done last week. And just all in all, the activity plan is just going to help us keep us organized and just keep us focused on what activities we need to complete in the future.
So at the end of the day, we're aiming for a safe landing of our payload at the Mars poles, a successful collection of the samples on the terrain, and analysis of the samples. And we're supposed to finish up with a elemental analysis of the ancient Martian atmosphere.
Did you stop recording now, Zach?
Right now.
Oh, nice. All right.
All right.
Okay, nice. So now when you end the meeting, it
Yeah.
would, your should be your